So hi everyone. Today we'll be discussing about what are machine learning design patterns, why they are required, and what are different types of machine learning design patterns. So let's get started. So while working on any machine learning or data science project, there is a set of common challenges that we face every day, like scaling data sets, maintaining reproducibility of a code, changing categorical data into numerical functions, etc. Now, if you go into the open space and explore solution for these challenges, it might consume a lot of time for you. Machine learning design patterns helps us in this case only. So they provide us with general solutions for some of the most common challenges that we might face in most of our data science projects. And eventually, after making a minor tweaks in this general solution, these solutions can be implemented in our projects very easily. So for example, assume that we wish to write a blog. So you are new to blogging and you wish to write a blog. So the first thing that you would do is to explore what structure you should follow in writing a blog. Assume that you figured out that okay, I need to have a heading, subheading, body of the blog, and a conclusion. So basically four parts in which you will divide a blog. Now what you did, you named this general design as a general blog. So this design name is given a general blog. Now assume that next time some another novice person comes who wished to write his first blog, he would again go back into the internet and explore okay, which structure I should follow, and again waste his time. Instead, what we can do is that we can provide him with this particular design, the journal blog design that we have built out after our exploration, and eventually that person, according to his requirements, can make minor tweaks and get started. Hence, he has saved a lot of bandwidth for himself. This is the whole idea of machine learning design patterns as well. So, whatever common challenges that we face in our day-to-day life, we would be having a general solution for all of them called as design patterns, and eventually, after making minor tweaks, these patterns or may not be, you don't even require any tweaks. uh, these solutions can be implemented directly in our projects. So what are the common challenges that we might expect? So let's explore that as well. So first of all is the data quality problem. Now data quality has majorly four facets. One is accuracy. How accurate is your data? For example, if it is supervised learning, are the labels of ground truth correctly labeled? Completeness, whether your data covers all the use cases that you might encounter. For example, in case of multi-classification problem, you may have imbalance in the data set while training, but eventually while in the real world this imbalance won't exist. And completeness of the data means that your data should cover all the different aspects of the problem very completely. Consistency, following the same standards, same rules across the whole pipeline. For example, usual problem that I have seen in classification problems is that we have different spellings for labels. For example, if you are classifying dogs and cats, you might have spellings like capital DOG, all capital dog, or all small dog. So they are having different spellings for the same label. Hence, there is no consistency in the data. Timeliness refers to the time lapse between an event occurring. Like for example, you have a deployed model in production, it gives you some prediction xyz. Now after the prediction is made, how much time is taken to save that data into data set? Like ideal situation would be you would wish to save this instantly, but it can be the case that there are certain other steps in the pipeline, which is why it might take some other time. So these are the four things that we consider in our data quality. Now, talking about design patterns to encounter problems covering in data quality, so we can discuss a few. Upsampling or downsampling the data to cater imbalance. So when you saw the problem for completeness, upsampling or downsampling can be taken as a general design pattern. Also, like when we talked about the consistency problem, we might begin with making all the labels in lowercase, so that whichever case you have in your data set, eventually all of them gets labeled to lowercase, and hence there is a standardization now. Again, these are just general examples how design patterns may look like. Reproducibility is also a very big challenge. So let's see some examples around how reproducibility, maintaining reproducibility is a bit difficult. So assume that like even if you have the same data, you have the same model, and you train the model on the same data set, so eventually it can be the case that your results may differ a lot in your first case and your second case. So you are using the same data, you're using the same model. Even then also, if you train it on like in two different time stamps, you might get different results. Why? Because weight initialization in models is different. It can be the case that in the first instance the weight might get initialized by some values x, while in the case of second, case the weights got initialized by some distribution y. Also not in just terms of the output is getting presented, even like when you have different systems with you that with the same data set and with the same model, your training time or your inference time may increase or decrease a lot. So if you have 4 GBs of RAM, if you have deployed a model on a big server with a lot of computation power, the training of the data set won't take much time, but in case of a resource like your personal computer, it might take a lot of time. So again, reproducibility should mean that every aspect of the pipeline should be reproducible, be it the training time or be it the output that are getting presented. Data representation, again, we can have like discuss a few of the problems that we might face in data representation, that is scaling the data set, bringing different feature values to the same scale, converting categorical data into numerical representation, skewness and kurtosis. This is again when the data set is not following normal distribution. A few of the design patterns that we can follow is like use some sort of an embedding for generating numerical representation for categorical data or one hot encoding. Or like in case of scaling, we can use some scalar method like standard scaler or min max. Again, these are all examples of design patterns. So eventually, we have a problem in our hand. Ki, okay, features need to be scaled, and we have a design pattern. Use some sort of a scaling algorithm or scaling method. Now, which method you choose, depends upon you. So data drift means that once you deploy a model in production, it can be the case that after some time your model becomes obsolete. The distribution of the target variable has started changing now. So earlier, like for example, assume that we are trying to predict the average income of an Indian in 1990s. So assume it to be X. Now in case of 2020, like after 30 years, like it's very obvious that the income levels have increased compared, because though inflation has come in, but the number in terms of magnitude has increased. So there is a data drift in the income variable that we have got. So hence your model has to be retrained. So similarly, concept drift is that the distribution of the variable doesn't change, but the relationship does. So for example, it can be the case that there is a variable x that used to depend on variable y linearly, but now after a few years, variable x is now dependent on variable y exponentially. So you're getting my point. The model that you deployed some time back was capturing the linear relationship. It was assuming ki, okay, between these two variables we have a linear relationship, but now as the relationship has changed, your model is of no use. Again, to curb both data drift and concept drift, we need to have some sort of a scheduler that can frequently uh, update your model, that is retrain the model with new data. Again, this is again a design pattern only to curve out data drift and concept drift. The last one being multiple objectives coming in. Like in real world, it's a very common problem that you might be training a model on a particular data set, but different business teams require different outputs. That is more of a modified version of your output. For example, assume that you're building an income predictor. Now, first business team wish key, okay, using the income, we need to classify, we need to have two groups, middle class and upper class. Second business requirement is they need to get the direct income predictions, and the third one being they need to get that cluster where Gen Z is earning more than X dollars. Now you can see that all these three can be built out of using your income predictor only, but we need to have some sequence of solutions. Like you will be first building, that would be sharing that income predictor model that you have, and eventually some wrapper sort of a thing for all the three businesses, some sort of a logic that we need to implement, giving them different results. So you can see that these are the different challenges that we face in our day-to-day life in machine learning problems. Now let's discuss about what are different types of design patterns. Data representational design patterns, or design patterns that revolves around how to represent the data to the model. So you saw that key how like what are different solutions for scaling, different solutions for categorical data, conversion of categorical data into numerical data. All of them lies in data representational patterns. Problem representational patterns, so patterns involving how to represent a particular machine learning problem for a model for training. For example, like if you are building out a model for predicting the ratings of a movie out 1 2 3 4 5, these are the five things. So eventually you can take this problem as a classification problem also, or as a regression problem also. So how are you representing this problem to the model for the training is called as problem representational design patterns. Model training patterns, like how are you training your model to get to the final output. So eventually you might be using checkpoints, you might be using at times overfitting the data would be crucial. You might be using transfer learning as well. So all these fall in the model training design patterns. Resilient serving patterns revolving around efficient deployment. So different methods that you can use for deployment, like setting up schedulers, you might have serverless deployment, all this following resilient serving patterns. And the last one being reproducibility design patterns that help us to reproduce our data, like setting up particular random seed while initializing weight, so that eventually whenever you are retraining your model with the same data with the same random seed, the weights get initialized with the same values. So you're trying to reproduce your output given when you're even retraining the model with the same data every time. So this is for now. We will be discussing different design patterns in the coming up video.